Good afternoon, everyone. And once again, welcome to webinar on structural nonlinear analysis. And myself, Ravindra Bucherla, and I'm working as an application engineer in Ansys team, in ARK Info Solutions Private Limited. So, so in this webinar, we are going to cover the topics related to nonlinears. And first, we'll start with, what is the major, uh, what are the major reasons that will cause the nonlinearity to any problem that we will solve, and what are the types of nonlinearities that we will be having, and so how we will use the Newton-Raphson method to solve our nonlinear problems, and basically how this nonlinear problem will converge, and if we face any issues while solving the problem, what are the different methods that we can approach to solve this convergence. So all these topics we are going to discuss, and along with that, we will be solving two problems. One is string analysis, and in this workshop, we majorly focus on structural nonlinearity because of the geometry. And in another workshop, we will mostly focus on the contact nonlinearities. So yeah. So before we move into these topics, I will just show you what are the different physics that we can solve by using Ansys software. So Ansys is a pure old software which have the capabilities to solve the problems related to different physics like structures, fluids, electronics, semiconductors, GMAX, photonics, optics. So these are the different physics that we can solve, and we have a cloud platform, and for materials we have advanced materials like where we will be getting more than 4,000 plus materials to solve any problem related to any of these physics. And yeah. So in this webinar, we majorly focus on Ansys mechanical. So before we move into the nonlinear analysis, I will just explain what are the different tools that are available in structures product family, and what are the major applications that each solver will have. So this is the complete product collection for the structures. Whenever we solve any complex engineering problem, we will be needing different kind of approaches. You can say sometimes we will be solving a problem related to static analysis or dynamic analysis. So in again dynamic analysis also we will be solving problems related to explicit dynamics, implicit dynamics. So for different analysis, we will be using different equations, and these are the different tools that we have in Ansys, which each tool has its major focus area and major application. So let's start with Ansys Mechanical, which is a flagship solver for structures which have the capabilities to solve the problems related to static analysis and linear dynamic analysis, and also it has the capabilities to solve the thermal related problems as well, and fracture mechanics, uh, fatigue analysis. So this kind of problems majorly we will solve by using Ansys mechanical. And LS-DYNA is a powerful explicit solver which have the capabilities of both implicit and explicit dynamics, but in almost mostly we will use the LS-DYNA for solving the problems related to explicit dynamics, like automobile related examples. If we take crash analysis, seatbelt analysis, airbag inflation, bullet impacts, or so this kind of explicit analysis we generally do by using this LS-DYNA tool. And when we talk about ANSYS forming is dedicatedly designed to perform the manufacturing operations like stamping, forming. So this kind of manufacturing operations can be done by ANSYS forming. And for multi-body dynamic analysis, where we will be having more than two components in our assembly, if you want to check the kinetic behavior of the assembly, or the rotations, gears, or any advanced multi-body dynamic analysis, if you want to analyze. So generally we will go with ANSYS motion if that assembly will contain both rigid bodies and flexible bodies. And so ANSYS Sherlock is a tool dedicatedly designed for PCBs. Um, if you want to design any PCBs or any electronic hardware, generally these electronic components will be having different type of mechanical loadings as well, like vibrations or thermal loadings. So what will be the effect of the components which are inside the PCBs because of this effect? We will be analyzing, and we will be improving the life of these components. And for additive manufacturing, we have dedicated solution, additive solution to minimize the risk of metal products while printing, and it has so many advantages related to optimization as well, related to lattice optimization, topology optimization. So this kind of optimizations and 3D printing related simulations and material analysis generally we will do by using these additive solutions. And Autoden is also an explicit solver, just like LS-DYNA. It has its capabilities, like mostly will be on impact analysis and explosion. But you can also solve the same problems by using LS-DYNA as well. So this is the major tools that we have in structures to solve different kind of applications. So in this webinar, we are using only the Ansys mechanical tool to solve our different type of nonlinear problems. So as I discussed earlier, generally in structures, we have this different type of analysis. So majorly it is classified as static analysis and dynamic analysis. Basically, whenever we solve any problem which have no dependency on time, so we will generally consider it as a static analysis. And for solving the static analysis problem, this is the equation that we use: F equal to K into U. So F is the force that we are going to apply, and K is the stiffness for that particular model, and U is the displacement that we will be getting because of this applied force. So this is the equation that we will use to solve all the problems related to static analysis. But whenever there is a time dependency, so obviously the inertia effects will also be included in that problem. So that problem we generally consider it as a dynamic analysis, where we will be having a mass matrix, acceleration, damping matrix, and velocity as well. So if the problem is depending on time, like if any one of the component is moving with some velocity, or if you are applying the load with respect to time, so like this kind of time dependency problems, we will be considering it as a dynamic analysis, and where it will be having the inertia effects as well. And again, the dynamic analysis will be divided into two types. One is implicit dynamics, and another one is explicit dynamics. So that is another topic we might discuss maybe in another webinars if we do anything on it. So the other equation that we will use to solve the problem related to thermal analysis is this one. So Q is the heat flow, and C is the heat capacity, and so this is the K is the thermal conductivity and temperature gradient. So this is the equation we solve. We use to solve the problems related to thermal, whether it is a steady state or transient thermal analysis. So let's see what is the nonlinear behavior. So generally, whenever we solve any problem, so whether you are solving a simple beam or a big structure, or some, if you are solving any hyperelastic material, or anything, like generally in structures, whatever the problem that you solve, if the problem is not depending on the time, so as we discussed, this is the equation that we will use: F equal to K into U. So in the 1600, Robert Hooke discovered a simple linear relationship between the force and displacement. So that is the force is directly proportional to displacement. Like whenever we apply any force to any component or anything, so the displacement will be linearly increased along with the force. So it means the stiffness matrix, the K will be a constant. So it will be a constant value. So if we apply the force, or if we increase the force, the displacement will linearly increase. Okay, so this obeys the linear relationship between this force and displacement. So generally we will call it as a linear analysis or linear equation. Okay, so this is true in cases like when the behavior of the geometry will not change much, or the problem that we are solving is doesn't have any deformation beyond the plastic limit or this kind of problems. But sometimes we will be dealing some kind of structures which will not follow this linear relationship. So in means like the stiffness of the model will change with respect to force. So whatever the force that we will apply, the stiffness matrix K will not be constant. So because of this reason, the deformation will not be considered as a linear increment with respect to force. So you know, so this is a difference between linear and nonlinear analysis. So in linear analysis, the stiffness matrix or the stiffness will be constant, and in the nonlinear analysis, the stiffness will not be constant. So the K is like okay. So I was explaining the different type of analysis that we have in structures. Majorly, we will be classified into two types. One is static analysis, and another one is dynamic analysis. So static analysis is nothing but whenever we solve any problem, if that analysis will not be depending upon the time. If we are analyzing any structure, and if the structure is not moving with respect to time, or if the force that is acting on the structure is not varying with respect to time, so generally we will consider that problem as a static analysis, and this is the equation that we will solve for static analysis. Like this is F equal to K into U. So F is the force that we are going to apply, and U is the displacement that we will be getting because of this external load F. So whenever our structure will be experiencing any motion in it, like if we have an assembly and if any one of the component is moving, or if any external load is acting on the body with respect to time, so obviously that inertia effects will also be included, and we will be considering that problem as a dynamic analysis. And this is the equation that we will be solving for dynamic analysis, where the mass matrix and acceleration, damping matrix, and velocity will also be included along with this F equal to K into U. So along with this F equal to K into U, we will be having the extra terms related to the inertia effects, mass into acceleration and damping effects will be included in the dynamic analysis. So again, depending upon the non-linearity and the time, the periodic time or the time that involved in this analysis, again the dynamic analysis will be divided into two types: explicit dynamics and another one is implicit dynamics. So yeah, so we will be in structures, we will be solving the thermal analysis as well. So this is the equation we will be using to solve all kind of thermal analysis, whether it is a steady state or transient thermal analysis. So according to Hooke's law, in 1600, Robert Hooke discovered a linear relationship between the force and displacement. So whenever we apply any force to any structure, so it will linearly give the deformation with respect to force. So as we increase the force, the deformation will also linearly increase up to some level. So this is F equal to K into U, so which will follow the Hooke's law, and we will be considering it as a linear analysis or linear structural analysis, as long as our structure will obey this rule, Hooke's law. So this linear relationship will not be true for all the cases. So there will be some cases which will trigger the component of structure to change its stiffness. So the stiffness K will change because of some reasons. So uh, so in that kind of cases, that the displacement that we will be getting because of the force will not be varying linearly. So you can see in this graph, you can see the stiffness matrix is changing, or the K is like not a constant, so it will vary with respect to the force. So the reasons behind the behavior, the reasons, reasons behind change the stiffness of the body will be because of the strains that are acting on the body because of the external force. And also if the body is experiencing any large deformations or large reflections, and if we have multiple components in our assembly, and if there is any contact between these multiple bodies, and if the contact is changing with respect to force or something. So these are the three major reasons the stiffness of our component may change compared to, like, initially it will be having different stiffness, and with respect to force it may experience different stiffness. So if we classify these three things into three different sources of nonlinearities, so the first one is geometric nonlinearity. So even if you are taking a material which is having the properties up to elastic limit, so if you are taking a linear material, or if there is no contact, means if you are analyzing only a single component which don't have any contact, means even if you don't have any material nonlinearities or contact nonlinearities, so still you will be facing you will be having the nonlinearities because of the structure. So that is geometric nonlinearity. So for example, if you take this fishing rod, so initially if it is not having much load in the fishing rod, so it might have some stiffness like K, and you can observe the force versus displacement equation here. So the point is the uh, point where we will be having the stiffness at this initial condition. But after getting some load to the fishing rod, the stiffness of the fishing rod may change as per the load. So it will give deformations with respect to force in a different way. So this might be the reasons, and you can also take a spring as a example. Like when we vary the load in a spring, like if you fix one end of the spring, and if on the other end, if you linearly increase the force, like 10 newtons, 20 newtons, 30 newtons, 40 newtons. So if it is a nonlinear spring, you can easily observe the change in deformation for each load. So how it is going to give different values. So this is majorly because of the geometric structure. So that is geometric nonlinearity. And another type of nonlinearity that we have is material nonlinearity. Uh, so whenever we apply any external load, and if we are getting the results or the deformations in our structure which is below the elastic limit, like the stress or strain that we are experiencing in our model is below the elastic limit, so obviously that is a linear problem. And if we are providing the properties beyond the elastic limit, like if you are giving the materials properties like plasticity or hyperelasticity, so if we are providing these kind of material inputs to our body or our structure, and because of the external load, the force that we are applying, if uh, the structure is experiencing the stresses beyond the elastic limit, so obviously we will be considering that as a material nonlinearity. And similarly, if the contact is changing, like if you are using any contact where like, for example, frictionless, frictional, or no suppression, so where the contact uh, between two bodies will change and it will generate some frictional force or normal force. So generally, the stiffness of the both bodies will also be will also change with respect to the contact. So that might be also the reason for the non-linearities. So these are the three sources that we will be getting the non-linearity in our structure. Uh, Sometimes all the three will be included in our problem, and sometimes only one or two things will be triggering triggering our non-linearities. So we will discuss about these things. Like in our answers, we will be enabling the loss deflection on while solving the problem to include the geometric nonlinearities. And similarly, if we have the material properties related to the elastic, like plasticity or hyperelastic materials, whether it is experimental data or theoretical data, and some test data related to Chabochi or creep, life, strength, or if you are using any material, any components of gasket or viscoelastic material. So this kind of material information, if you are providing to our structures, so generally it will be considered as a material nonlinear problem. And similarly, we will be having five type of contacts between whenever we have any assembly where the two bodies are sharing the contact. So out of this 5, two contacts will be considered as a linear contact, and 3 contacts will be considered as a non-linear contacts. So if we are using the bonded contacts, means if two surfaces are completely tied or fixed, so that is a linear contact. And no separation means the point of contact between the two surfaces may change, but these two surfaces will not separate. So these two type of contacts will be considered as a linear contacts or linear analysis. And if you are using any of these 3 contacts, whether you are using a frictionless contact, rough contact, or frictional contact, so these 3 type of contacts will be considered as a non-linear contacts or non-linear analysis. Okay. So yeah. So whenever we have any of these 3 non-linearities, as we discussed, our stiffness matrix will change with respect to force. So how we are going to calculate the updated stiffness for each problem will be by using this Newton-Raphson method. So uh, in this Newton-Raphson method, instead of solving the problem at a single iterations, it will go multiple iterations, and it will automatically calculate the updated stiffness, and finally we will be getting the result. So I will just give you little more understanding like how it will solve. So suppose we are analyzing one structure. So we are analyzing the structure, and suppose we are applied some boundary condition and some load on it. This is F applied. Okay. So if you observe the force versus displacement. Okay. So if the stiffness behavior of this model is initially, let's suppose we will be considering it as a K. So if the stiffness of the body will not change, then it will be considered as a linear analysis, and we can easily solve the problem. Like it will be a straight line. Okay. But in case if we have any non-linearities, like if you are using any material which is having the properties beyond the elastic limit, or if the structure will experience if the structure itself will be having some non-linearities, or if we are having multiple bodies, and if we are using any contact non-linearities, then the stiffness of our body K will not be constant throughout the procedure. So it will vary, like whatever the initial value of initial stiffness is there. So that might not be that might not be maintaining the till end of our problem. So it might change with respect to force. So this like I will explain how this is going to be calculated. Okay. So let's see, like force that we are going to apply is, so Fa is the force that we are applying. So this is the applied force initially, and okay. So let's assume K is the stiffness that we will be having initially. So it will let's say, like, no, this is the K. This is force applied, and let's say this is the K, and so because of this force applied and the stiffness K, so we will be having the deformation x1. So x1 is the displacement that we are getting because of the applied force F. So this will be the stiffness K that we will be having initially. But if after applying the force, it will be having some deformation, stress, strain, or anything, and after that the stiffness K will be updated to some other value. So because of that, whatever the force that we will apply and the reaction force that we will be getting will be different. So because of the change in stiffness in our model, so we will be getting different force reaction. Let's say, so this is the F1B, the force reaction that we are getting. So first we will apply the initial force, and for that initial force and by taking the initial stiffness, we will be getting the displacement x1. Again, based upon the displacement that we are getting, we will calculate the force reaction. So for this applied force, we will get the displacement x1, and from this displacement, we will calculate the force reaction. So this force reaction F1 and F applied. So the force we applied and the force reaction that we are getting will be equal if the stiffness K is constant. Means after applying the force also, if our model will not, if our model stiffness will not change, so if the K will not change, then the force applied and the reaction force that we will be getting is equal. But if the stiffness will change because of these three non-linearities, then the force reaction that we get and the applied force will not be equal. So that is why F1 will be somewhere and Fa will be somewhere. And again, we based upon this force. So based upon this force, again we will calculate the stiffness. So again we will calculate the stiffness, and let's suppose this is the stiffness that we are getting. Okay, so in this, let's suppose this is K1, and let's take this is K2. Okay. Okay. So again, we will apply the same load Fa, and we will be getting some deformation x2 for the stiffness K2. So for the stiffness K2, again we will be getting the displacement x2, and again we will be calculating the force reaction F2. F2 we will calculate, and again based upon F2 value, again we will calculate the K3. And from K3 again we will apply the Fa value, and we will be getting the deformation x3. So again we will calculate the force reaction, and again we will get F3. So like that, from F3 we will calculate the stiffness K3. Okay, yeah, K3, like that we will again calculate the stiffness here. So like that we will be getting the nonlinear stiffness. Oh, okay, so whatever the updated stiffness, the graph we will be getting by using this Newton-Raphson method. So when we get, suppose if we apply the force Fa for K4, suppose K4 is another stiffness that we got, and x4 is the displacement for that. So for the x4 displacement, if we get a reaction force F4, so when F4 will become equal to Fa, then we will be considering the solution is converged. So whenever the applied force and the reaction force that we will be getting is equal, then we will be considering the solution, means the solution is converged. Okay. So this is how we will be calculating the stiffness matrix. I will just explain once again. Okay, so I will just explain once again. So initially, if we have K1 or K as a stiffness matrix, and after applying the force, we will be getting the value x1. So as a displacement because of this applied force and because of the stiffness initially that we got, and from the displacement, we will calculate the force reaction. So we will calculate the force reaction from the displacement that we will be getting because of this applied force. And from this applied force, we will be calculating the stiffness again. So again, we will use, suppose, we will be using FA equal to K into X1. So here FA is known and K is known and X1 is unknown. So we will be getting that value in the first solution. And from X1, we will be calculating the force reaction. So we will be calculating the force reaction. And now once we got the force reaction and the displacement, we will be calculating the K1. So based upon the K1, again we will calculate the displacement for the like after applying the force, applied force for the stiffness K1, we will be getting another displacement K2 or X2. So this will be X2 and the force reaction will be like again we will calculate the force reaction F2, and from this force reaction we will calculate the stiffness matrix. So like this, by using the Newton-Raphson method, we will be getting the stiffness, updated stiffness, and when F1 and the force reaction that we will be getting is equal. So ideally, this is the ideal case, like the force applied and the force reaction that we are getting is equal. Then we will be considering the problem as the solution is converged, and at this point, so whenever we have the force applied and force reaction equal, so whatever the displacement that we will be getting, that might be x4 or x5, whatever the displacement, so that displacement will be the correct displacement. So this is the ideal case. The force applied and the force reaction that we will be getting is equal, but it might not be possible in the numerical analysis. So that is why we will be considering the criteria to converge the solution. So I will explain about that as well. I hope you got some idea. Like this in the first, you can see force applied and the displacement. So this first line or the slope is k initial value, and from that we will be getting a u1. And at this point, again, we will be calculating the force reaction and we will be getting this slope. So like that, we will be getting this stiffness value. So the stiffness value will be getting updated. So like this. So we will be solving this problem by using the Newton-Raphson method. Okay. So the same thing that we have discussed, the force applied. So this is the first K matrix. So F1 we applied and we will be getting the X1. And again we will calculate the stiffness matrix and applied force, so x3. So like that we will be getting this equation. Updated stiffness matrix will be calculated like this for all kind of nonlinear analysis. And okay, so just I will solve one problem, and you will understand clearly how the stiffness matrix will influence the analysis. So I'm taking one spring structure. Okay, so I hope you all knew about Ansys platform. So this is the Ansys workbench where we will be solving all kind of structure and fluid problems. So we are taking static structural for structural analysis. And if you want to solve any problem for explicit dynamics, you can go with explicit dynamics or harmonic. Like if you want to solve any problem related to vibrations, you can go with harmonic response or random vibrations or response spectrum. Okay. So whatever the analysis that you want to do, you can pick the analysis system from the analysis here. And for all kind of structural analysis, this is the flow that we will follow. So total, there will be 7 steps to solve any structural problem, whether it is a static analysis, explicit, harmonic, response spectrum, random vibration, whatever it is. So the first step will be selecting the analysis system that we need to that we will be using in our project. So let's suppose if you are going with the static structural, so you can select the static structural, and the next step is engineering data. So if you double click on engineering data, so by default structural steel will be there. In case if you want to add any new material, you can go for engineering data sources. So where all the materials will be divided into different libraries based upon the application. Like if you are solving a problem related to additive manufacturing, you can click on additive, and these are the materials which are available for additive manufacturing. So if you click on geomechanical materials, then geomechanical materials will be available here, like chalks, dolomite, limestone, so this kind of materials. So if you click on general nonlinear materials, so here we can see these are the nonlinear materials. If you want to add aluminum alloy, you can click on this plus symbol. If you want to add concrete or any material, you can click on this plus symbol. So once you click on this plus symbol, automatically book symbol will appear. That means this material is already a simulation. So similarly, you can add any library as well by importing the .xml file. So the material file that Ansys Workbench will support is in the format of .xml. So if you have any material file, you can click on this .xml and you can import the file. Okay, so you can see these are the materials. So okay, so if you have the properties like density and isotropic elasticity, so that means so let's suppose if we see the stress strain graph. So if you see the stress strain graph, the graph will be somewhere like this, or like for different materials it might be different. So up to elastic limit. So up to elastic limit, we will be considering the properties of density. Even for static analysis, if you are not using the standard earth gravity, there is no need to include this density and isotropic elasticity. So these two properties, if you provide, that means we are giving the information to our analysis up to elastic limit. So this will be considering as a material linear. So if you provide only the properties up to this point, that will be considering as a material linear properties. And if you provide any property which is related to hyperelasticity, like hyperelastic experimental data or hyperelastic this any of the material model if you use, or if you use this uniaxial plastic strain test data or plasticity properties, creep, life, strength, gasket, viscoelastic properties. So if you use any of these properties, like in this case, we use one plasticity, bilinear isotropic hardening. You can see this. So if you are using or if you are giving the properties beyond this limit, like that might be the plastic or hyperelastic or whatever the property. So these properties, if you are providing, that means we will be considering the material nonlinearities. So this is material nonlinearities we are considering if you are providing the properties beyond this elastic limit in the engineering data. Okay. So the next The third step will be the geometry. So generally we will import the geometry, and once we import the geometry, or if you want to create the geometry by using this any of the tools like space climb, discovery, so any of the tools you can use, and you can go to the model. Okay, so yeah, once we click on the model, it will open the mechanical window where we will be following this structure to solve our problem. So let's see how this structure will help us. Like I'll just explain the details. Like I assume you knew little about this Ansys platform to solve any problem. Okay. So this is the geometry. So inside the geometry, we will be having the components. If you have 4 components, all 4 components will be available here. In our case, I have only one body, that is surface body. Once I click on the surface body, the details of the surface body will be visible here, like the graphic properties or the definitions, like whether the body that we are considering is a shell or a beam or something like that, and the stiffness behavior like rigid, flexible, or gasket, and the material that we are going to use. So whatever the materials that we added in the engineering data will be visible here. If you want to add aluminum or concrete or copper alloy, whatever the materials that we added in the engineering data will be visible here, and you can assign that material to a component. And if you want to consider the nonlinear effects, you need to click on S. And also because of the temperature change, whatever the thermal deformations and stress strains we will be getting. So if you want to considering that effects also, we need to enable this thermal strains as effect. Yes. So by default, these two things will be considered as a SS only. There is no need to change. And these are the bounding box properties and the properties related to volume, mass, centroids, moment of inertia of our geometry. And this is the number of nodes and elements that we will be having after generating the mesh. After generating the mesh, the number of nodes and elements that will be available here, we can see this. So this is the materials that we added. If you want to read the properties, we can read here. Okay, and after generating the mesh, so you can right click on static structural and insert the loads and boundary conditions that we want. Whether you want to insert any accelerations, earth gravity, rotational velocities, pressures, force, movement, thermal loads, fixed support, remote displacement. So whatever the supports and loads that you want to apply for your model, you can insert here and you can apply to the model. So I already applied the fixed support to the bottom edge. So on this edge, I applied the fixed support. And on the other edge, I applied a force of 250 newtons. So 250 newtons force I applied here, and I applied the fixed support. So fixed support and force I applied, and I am considering the structural steel as a material. Okay. So after applying, let me insert deformation or stress or anything, and let's solve the problem. So we are not focusing much on how to solve the problem. We are focusing here only on the non-linearities. Okay. So you can see after applying the force of 250 newtons and giving the fixed support here, I am getting a deformation of 37.55. Okay. So here we can see from 0 to 250 newtons, if I apply the force, it is getting deformed, and the total deformation that I am getting is 37.551 mm. So this is the deformation that I am getting because of the applied force of 250 newtons along x-axis. So here, as I discussed earlier, if you want to consider the geometric nonlinearities, you need to enable this large deflection on. Okay, so let me duplicate this one. So in this case, this is a linear problem because I didn't enable the loss deflection on. So because of this linear problem means the stiffness K is constant. You can say, when I apply F equal to K into X. So F is here 250 newtons, and for value K, I am getting 37 point something, 37.55 mm I am getting. So this is the deformation that I am getting for stiffness K. So here K is constant. Okay, so in this case, let me. Okay, so I just duplicated the same static structural and I'm opening the mechanical model once again. Yeah, so here in this case, the only thing I did is I will enable this loss deflection on. If you are going with the geometric nonlinearities, you need to enable the loss deflection on. So if you enable the loss deflection on, you will be having the nonlinearities because of the force. Okay. So nonlinearities of force convergence, moment convergence, displacement convergence, rotation convergence. So all these four type of convergence will be, will come under this once we enable the loss deflection on. If you don't enable the loss deflection on, the constant, like the stiffness will be constant. If we enable the loss deflection on, the stiffness K will change. Like this is the K1, this is the K1. So if you go to solution information here, so here you will not be having any data related to force convergence, moment convergence, displacement convergence, or anything, because this solution didn't go in a iteration manner since the stiffness K is constant. Okay, so let's solve this problem after enabling the loss deflection on. Yeah, so it is solved. Now, if you observe in both models, so if you observe here 37.55 is the deformation that I got, and here I got 31.128. Okay, so there you can see the difference. So for the same load that we applied, so 250 newtons, we applied the same load, but we are getting 31, okay, yeah, 31.128. 31.128 is the deformation that we are getting because the stiffness is changed. The stiffness of the model is changed. Because of that, we got this different deformation. Okay, so let's see the force convergence that we discussed. So here, if you come to the solution information, so here you can see force convergence is available, displacement convergence is available, moment. So this convergence are available here in nonlinear analysis. But in the linear analysis, there is no data is available for any of these things because only one equation is solved, that is F equal to K into U. But here, instead of solving directly, it will went for convergence, and you can see this. Okay, so this is what we are talking about: force convergence and force criteria. And also there is one more thing called bisection substep. So I will discuss about this more in detail. So force convergence is nothing but, you can see for one, like for the initial step. Okay, let me take. So for the initial step, it will be getting some value. Okay, so once it is solved, the force applied, so we will be getting the force reaction. So the difference between these two things, so the force applied and the force reaction that we are getting, the difference between these two is not equal to 0, then like whatever the force that we will be getting, so that is a residual force or the value of the force convergence. Okay, so this is the value that we will be having here. Okay, and you can see force criteria. So force criteria is this value. So force criteria is nothing but, like, in order to converge the problem, it supposed to be 0, Fa equal to F1, but this is not possible. Like, this is not possible. Fa minus F1 is not possible. So that is why we will be taking some criteria, okay, force criteria. So instead of Fc equal to 0, we will be considering some value, because numerically that is not possible to take. It will take a lot of time. So we will be considering some value like 0.001 or 0.112 based upon the force we are applying, and based upon the reaction force we will be getting this value. So that is the force criteria. So you can see when this force convergence is less than or equal to force criteria. So when this value, so the force applied and the reaction force that we are getting is less than or equal to force criteria. So less than or equal to force criteria, that means the solution is converged. Okay, so you can see this is the point at 15. At 15th iteration, the force applied minus reaction force is less than the force criteria. That is why this step is converged. Okay, sub-step is converged. So I will explain about this divergence as well, or divergence or bisection as well. But first, let's focus on the convergent points. So similarly, you can see here, when the force convergence is less than the force criteria, you can see this step is converged, this step is converged. So like this. Okay, so like this, when our problem will meet this criteria, so it will automatically converge. Okay, and yeah, so you can see the difference between this non-linear problem and linear problem, that the deformation that we will be getting is not true if the problem is a non-linear problem. Okay, so just yeah. So if you come to analysis settings, so here we will be seeing some things like, number of steps, current number of steps, step end time, and auto time stepping. So first we will see these four things. Okay, so I applied a force of 2500 newtons in a single step. Means at time 0, the force that we are applying is 0. When it reaches to 1 second, the force applying is 250 newtons. So you can see this graph from 0 to 250 newtons and 0 to 1 second. So we are applying the force linearly from 0 to 1. Okay, so only one time step is, we are considering only one time step, that is 0 to 1, and we applied a force of 0 to 250 newtons here. So if you want to apply in multiple steps, you can use this value. Like if you want to apply in 5 steps, and suppose the step will end at 0.2, first step will end at 0.2, 0.4, 0.6, and 0.8, and 1. Okay, so we are applying the same force, like in terms of 5 things. That means 50, 100, 150, 200, and 250. So you can see I applied, in the first problem I applied in a single step, from 0 seconds to 1 second, I applied 250 newtons. But but now I modified, like from 0 to 0.2 second, I applied 50 newtons. From 0.2 seconds to 0.4 seconds, I applied 100 newtons. So like that, I gradually increased from 0 to 250 newtons, from 0 to 1 second in step manner. So let's solve once again. So the same force, same time, everything is same. Only the thing is I took more time steps. Okay. So if you see the same force, so if you observe the same force criteria, and if you see the results are same, so whatever the result that we got in the previous solution and this solution is same. But if you observe how the solution is solved, so if you observe how the solution is solved, so it's solved, you can observe. So this is 0 and this is 1. So from 0 to 0.2, it is solved. Once the solution is converged, it increased from 0.2 to 0.4. And again, it's solved. Once the force convergence is less than the force criteria, it converged, means it shifted from 0.4 to 0.6. And again, it solved. It shifted from 0.6 to 0.8. Again, it solved. The blue color line indicates the step, means 0.6 to 0.8 to 1, it is got solved. So like that, step by step also we can solve. This problem will eliminate the bisection. So just I will take screenshot of this, and again I will solve the previous one. Yes. So if you observe the difference between both the solutions, okay, let me open the screenshot. Yes. So if you observe, I gave the load in step manner from 0 to 0.2, again 0.2 to 4, 4 to 6, 6 to 8. So like that I gave. The solution is converged like this. But if you observe the current solution, you can see the force that we applied is 250 newtons. The total load is applied, and it came to this point. Okay, it came to this point, and it got diverged. So the solution is diverged, means here what happened, let's take one. Yeah. So here initially it applied 250 Newton load, and it is trying to solve for that 250 Newton load, but it is not converging. Like instead of converging, it is diverging. Like the solution is not converging. So instead of converging, if you observe here, so instead of converging, if the solution diverges, if the solution it diverges in opposite way, then what it will do is, instead of applying 250 Newton as a applied force, it will apply. So you can see, from instead of 0 to 1, it came down. It came down to 0.5. Let me show you the solution information. Okay, so you can see in the first iteration, So you can see the first iteration, it is solved here. And here we can see there are 4 type of convergence. So one is force convergence. So you can see this is force convergence. So this is the value, the difference value, if force reaction minus the force applied minus force reaction, and this is the criteria. So similarly, the moment convergence is there, displacement convergence is there. So again, 3 type of convergence here in the second iteration, third iteration, fourth iteration, fifth iteration, sixth iteration, but nothing is converged. So what it happened, bisection happened. Now, instead of taking a time step as 1 second, it took 0.45 seconds. So instead of applying the force as 250 newtons, it took 250 newtons into 0.45. It is somewhere. Okay, so 112. So it applied only 112.5 load, and in between this range, it started solving the problem. So now the force applied in this step is 112.5 newtons. Because this solution is diverging, that is why bisection happened, and it took only 112.5 newtons here. So 112 newtons it took, because as per the time I calculated, and again it solved, and again it solved. And now you can see in first iteration, force convergence and criteria is not less than or equal to. So it is not converged. Moment also not converged. Displacement also didn't converge. In the second iteration, displacement converged. You can see converged. Means the displacement convergence value is less than the criteria. So if this value is less than this value, the step will converge. Only for displacement it converged. This value is less than this value. Similarly, in the next step, it didn't converge. Again, in the next fourth iteration, you can see moment convergence is this much and criteria is this much. So this value is less than this value, so converged. This value is less than this value, converged. So again, fifth iteration went, force didn't converge in all these steps, if you observe. But finally, the force in the iteration 8, force is not converged, but moment and displacement converged. And in the iteration 9, the force converged. So the force value is less than the criteria value. So force is also converged, and we got the that substep is solved, and again it went to next time step. Means now it is applying 0.275 increment to the time. Means let me a new one. Okay. So substep happened and it solved till 112.5, and again it got some time increment. Again now it is solving for this step. So some f equal to something, but that is also less than 250 only. Okay, so like that it got solved. Again the time increment is 0.1 second, and it you can see when the force is converged, again 0.1 time is increased. So like that it is got converged, the solution got converged. So like that you can see the solution got converged 0.5. So this is how the solution will converge, that F equal to K into U, the force criteria it need to meet. Okay, so you can see that in all the solutions, the criteria means the thing that we are talking about. Okay, the criteria 1.10 it is there. So that is nothing but FA minus the force reaction. Instead of 0, we will be taking some value. So that is force criteria. So this value the system will automatically take, or if you want to give on your own, you can also give on your own. So you can go in automatic or you can go by manual. So I will tell how this force convergence you can give. So if you come to analysis settings again, and here you can see the nonlinear controls. You can go for Newton-Raphson method. So here there is three types. The first one is full. So the full means like the one which we are discussing is the full one, and the initial one is there is one more thing called initial. Initial means, so I will just explain the initial, so you will be getting an idea about that. So initial is nothing but suppose if force applied, so you will be getting the x1, and this is k. So this slope is k, and you will be getting the force reaction F1. So now for the force reaction F1, it will not change the slope. So whatever the slope it is there here, it will just shift to this one. So the slope of this one, the slope of this one, and this one is same. So it will just shift to this point, and again it will solve the problem, and you will be getting x2, and you will be getting f2, and again the same slope you will be maintaining. So like that the solution will converge. So this Newton-Raphson method we call is initial. So we always consider the stiffness, whatever stiffness slope is there for initial one. So we will be considering that one. So this method we will be calling is initial. Okay. So full means the one which we are discussing till now, and modified means the combination of both, or hybrid you can say. It will be having the initial and the modified stiffness as per the requirement. And the unsymmetric means if the if the nonlinearity is very high, so the stiffness may go in the downward slope as well. So it is unsymmetric. And if you talk about program control means the criteria will automatically calculate. If you want to give on your own, or if you don't want to consider the criteria, you can remove or you can make it on. And once you make it on, you can give the reference. So this is the 0.01 is the value for FA minus force reaction less than or equal to force criteria. So this force criteria, if you want to give 0.01 manually if you want to give, you can give or you can enter here. Okay, the tolerance means little bit less or minus it will be considering. Okay, so you can give the tolerance and reference, the criteria to convert this problem here. So whatever this equation that we are solving, so you can give this value here, or you can go on program controlled. So similarly, the moment convergence will be there, and you can also mention the value, reference value, tolerance, so like that. So you can go program controlled. If you give more criteria, if you increase the value, you will not be getting the good results. Okay, let's see the other convergence. So displacement convergence. So this is displacement convergence. Displacement versus time, and moment convergence. Okay. So this is how we will solve and how we will be taking the time steps. Means sometimes we will not be the solution will not be solving, so it will go by section. Means instead of taking 0.0 to 1 second, if it is not able to converge, it will go by section, and again it will take some in between 0 to 1, like 0.45 here it took. So like that it will solve and it will go. If you don't want to face these bisections, you can go maximum number of time steps. So the load you can vary. Instead of giving the entire load from 0 to 1 second, you can give 0 to 0.2, 0.4 like that, and you can solve the problem. Okay. So just I will explain about yeah, stiffness. Okay. So this I think, I hope you got some idea about the geometric nonlinearity. So the whatever the thing that we are doing, this is the completely geometric nonlinearity. So if you want to go with the material nonlinearity, you can replace the material which is having the properties of this thing. So that is material nonlinearity. So now I will just explain about contact nonlinearities in 5 to 10 minutes. I will close the session. So this is one problem in which we are having two components, and these two components are sharing a contact between these two bodies. Yeah, so I will just explain what are the loads and boundary conditions that we applied. So here we have two components. So one is the bottom body surface and the top body, and these two bodies are sharing the contact here. So here it is having a contact. So you can see that the type of contact between these two bodies is, I'm considering it as a frictionless, but basically here we will be having four types. One is bonded, no separation, frictionless, rough and frictional. Just a second. Okay. So suppose if we apply any load, so suppose this body is fixed to the ground, and on the top of it there is one body. And if you apply any force, like any force to this, so the type of contact between these two bodies is complete. The contact between these two bodies are fixed. Means by applying some gum or something, welding or something, if these two bodies are connected completely, that is bonded. Means there is no sliding. So there is no sliding or separation. Means this body will not move in any direction, and also this will not move in top direction as well. It won't move in this direction or in this direction. So there is bonded, means no sliding or no separation. And similarly, there is one more contact called no separation. No separation means, no separations means it will not separate. These two bodies will not separate, but it will allow the sliding. So sliding will be allowed. The point of contact between these two bodies may change. So similarly, frictionless. So in the frictionless, sliding will be allowed, and also separation will be allowed. Okay, so similarly for frictional also, sliding will be allowed and separation will be allowed. But additionally, there will be one frictional force will be acting on here. So frictional force will be acting for the frictional. So that is the only difference between the frictionless and frictional. And for rough surface, there will not be any sliding. There will be no sliding, because whatever the force that we will apply, that entire force will be, balanced by the frictional force. Since the frictional coefficient value will be maximum, that is 1. So that is why this is F equal to normal force equal to nu into, okay, frictional force equal to mu into n, and this is normal force, and whatever the force, so the complete force will be applied here, F equal to n. Okay, So the frictional force equal to normal force. That is why there will not be any sliding, but separation will be there. Like you can take off this body, but it will not be sliding. Okay. So these are the 5 contacts, and out of 5 contacts, the status will be changed in these 3 contacts. So these 3 contacts will be considered as a non-linear contacts. So if you are using if you use frictionless, rough, or frictional, so if you use any of these 3 contacts, that contact will be considered as a non-linear contact. So even if you, okay, so that so yeah, here we applied pressure 5 megapascal pressure to the top body, and the bottom body is fixed. So because of this applied pressure of 5 megapascal, we are getting the deformation of 0.330 along x-axis. So along x-axis, we are getting this much deformation, and at the contact, you can see there is some small sliding is there, and this is the pressure that is acting on the contact. So at the contact, this much pressure we are getting, and there is some no penetration. So between these two bodies, there is no penetration. And along y-axis, this is the stress that we are getting, normal stress along y-axis. Okay, so yeah. So here also, if you use any of these 3 contacts, whether frictionless, frictional, or rough contacts, so again the solution will go in iteration manner, and it will solve like this by force convergence, force criteria, and so like this. Okay. So the detection method between these 2 contacts will be formulations. So the formulations and detection method, I will just give some overview about it. So as we discussed, we will be having bonded, no separation, frictionless, and rough, and frictional. So these 3 contacts will be considered as a non-linear contacts. And so you can see this is how if there will be 2 phases, right? One is contact and another one is target. So when there is a when we apply the force to the contact, and it will be in contact with this target, and a contact will be generated, like it will be in contact between these 2 bodies here. So if we select, if we give any contact between these 2 bodies, there will not be any penetration. But if we don't provide the contact, so these 2 bodies will interference if we don't provide the contact. So the type of detection between these 2 bodies will be totally 5 types will be there. One of them is pure penalty. So pure penalty is nothing but suppose a normal force will be there, and it will allow some small penetration, and whatever the penetration it is there, in that penetration there will be some stiffness will be like k normal stiffness will be generated, and according to this penetration and normal stiffness, the reaction force will be calculated here. So this is pure penalty. It will mostly use this will mostly use for the bonded type of contact. So in the bonded type of contact, it will allow some small sliding, small penetration to calculate this force reaction. And another one is normal Lagrangian. Instead of the reaction forces here, the pressure will be calculated, and mostly there will not be any penetration between the contact nodes and the target nodes. There will not be any penetration. This is normal Lagrangian. Okay. This is augmented Lagrangian. So here there will be one extra term called augmented Lagrangian, like additional to so equal to k into x. So this is not the force that we applied. This is not the deformation that we are getting. This is penetration, and this is the force reaction. So additional to this term, this is Lagrangian, and in augmented Lagrangian, we will be having one extra term lambda. So if the contact is normal, Lagrangian will be good. If the contact will be having some kind of sliding or something, so augmented Lagrangian will be the best formulation to get more accurate results. So this lambda is missing in this equation. And for the bonded coin, multi-point constraint will be there. Like automatically, this entire region will be restricted to go for penetration, and we will be getting the result. This kind of MPC formulation will be possible only for the bonded and no separation. And the detection method, the nodes that on both faces, the detection method will be a few things like based upon ghost points, the contact will be detected, or normal to normal form contact, normal to normal or to target. So nodal projected non-form contact. So these are different detection methods of the nodes that are available in both the surfaces. Okay, so one more important thing is, so this is trim tolerance. So trim tolerance is nothing but if there is any elements which are selected in the contact, which with but there is no contact between means that elements are not involved in the contact, the extra surface that we will be selected automatically will be trimmed. So it will reduce the simulation time, and you can give the tolerance as well, like up to what distance. See, this surface and this surface is not in contact with each other. Even if you select this surface, that will be trimmed. That will not be considered for the calculation. You can allow up to some tolerance, and you can remove the unnecessary elements. So in the left image, all the elements are selected. In the right image, only the elements which are, in big contact will be selected, and remaining things are neglected. So that is the trim contact. It will help you to reduce the simulation time. Like this is pure penalty and Lagrangian formula, and this is augmented. Okay. So this normal stiffness that we are talking for Lagrangian, yeah. Okay, yeah. So for the normal stiffness, F equal to K into X. So it will be multiplied with some factor. So normal stiffness factor, it will be multiplied with some factor. If you are going with the bonded or no separation, by default it will be multiplied with 10. If you are going with the nonlinear thing, a nonlinear type of contacts, it will be multiplied with 1. So that means this F equal to K into X will be multiplied with N. So here also N. Okay, so for nonlinear contacts, N value will be 1, and for linear contacts, it will be like by default, it will be 10. So how it will, this N value, how it will affect, I will show, and we will close the session. Yeah. So these things we discussed, different type of formulations, pure penalty, augmented Lagrangian, MPC, normal Lagrangian, beam kind of functions, and the detection methods. So whatever the nodes that are available here between these two bodies, the detection of the contact will be whether Gauss points or combined, these things will be there. Okay, so this is pinball region. That is, if two surfaces are having some gap, and still if you want to generate a contact between them, you can use some pinball region. Okay, if you go with augmented Lagrangian, penetration to no, yeah, normal stiffness factor, you can go for program control. If you go for program control, the value will be 1. And if you want to give factor on your own, like let's give 1 and let's solve the problem. In this equation, F equal to N into K plus lambda. So I keep 1 now. So for 1, I'm getting some pressure and there is some small penetration. So you can see there is some small penetration. So this is how it will affect. So if I give the N value 0.001, you can see the difference in the penetration. Means if if we decrease the n value, the stiffness will decrease, and it will lead to the penetration. So the penetration between the surfaces will be more if the stiffness is very less, and if the stiffness is more, the penetration will be less in the augmented Lagrangian. So augmented Lagrangian will help us in terms of very highly nonlinear cases, which will not be which will not be solved by using the normal Lagrangian. So if you go with normal Lagrangian, the penetration will be 0. If you go with augmented Lagrangian, there will be some penetration. That penetration will depend upon the factor that we multiplied with the stiffness. So this is, you can see, if we go with very less number, penetration is more. If we increase the stiffness as 10, the penetration is less. So for the frictionless or frictional or rough contacts, you can use these things for nonlinear analysis. Okay, so we already crossed 8 minutes. If you have any queries, we will discuss now. Closing the session. So if you
Hello.
have any queries, you can unmute and you can
Yes.
ask. Yeah. Yes, sir.
Yes, sir. Thanks a lot for such a wonderful presentation. Sir, I am having a few doubts. Like if I am doing a displacement control simulation process of indentation of soft materials. So
Okay,
from here, I will get the output data of like load versus displacement, because we didn't get any kind of load. So here we have to find it out through reaction force, or some other force we will get.
means may I know how you are going to apply your load if you, in order to
No.
get the force versus.
I am just doing the simulation in displacement control method, sir.
Okay.
Yes, sir. Because I think in Abacus we will get directly, but in Ansys how we can get the load output data if we are going to apply displacement?
Yes, sir. You will get wherever you apply the displacement in the loads and boundary conditions, you can drag and drop into the solution automatically. The reaction force you will get there, or you can insert the probe to get the force reaction.
Yes, only this is the only way we will get the force. Nothing
Yeah.
nothing else.
Yes, sir. Yeah. Wherever the boundary conditions are there, in all the phases you will be getting these force reactions.
Okay, and sir, one more problem we are getting while simulating my problem, that like they are going to tell many number of times you have to increase your load steps, or you have to decrease your displacement data. So how we can get a better solution to that one?
Yes, sir. If you are using any kind of contacts,
Yes.
like nonlinear contacts, you can change the formulations, or you can basically, if the solution is not able to converge, you need to go with the substeps.
Yes. So
So as we
it's
discussed,
yes.
yes, sir. So we can increase the maximum number of steps, and in each step also you can go by providing the substep in each time step by based upon the substep or time increment you can select, and you can provide the substeps.
So sir, is there any process to give the sub steps, or we have to give by our own, like initial, maximum, and minimum sub steps?
The program control you can go with, but up to some level only it will be useful, program control. If it is highly non-linear case, we need to give it manual.
Yeah. Actually, my problem is high non-linearity, sir.
Yes, sir. You will be getting the information in the solution output at what kind of, like, what is the maximum.
In errors, I am getting that kind of problem.
Yes, sir. Yeah, in the errors you will be getting the information at which time step it is not able to convert. And
yes,
what is
even the element is going to be distorted at that time.
Yeah. I think, sir, are you using any hyperelastic material?
Yes, sir.
Okay, sir.
I'm
So in
using
that case,
different kind of models.
Yeah.
Like
So in
Raman
that
model,
case,
NH model, and Ogden model, and all.
yes, sir. So in that case, basically you can go with nonlinear mechanical.
Yes, I'm using this one only.
Yeah, and another thing is there is one more option called mesh adaptivity. nonlinear mesh, nonlinear adaptive region. You can try this. I'm not sure about Abacus. What it will do
Okay.
is whatever the element that is getting more distortion,
Yes,
so that
yes,
will be remeshed on the criteria at substep level. So it
yes,
will
yes,
avoid the problem. This kind of issues will be avoided by using this thing. Like you can go with the nonlinear adaptive region, or you can go with nonlinear, non-mechanical. You can use if you are using any hyperelastic material, and also you can try
yes.
with element order linear.
Okay, 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 okay.
So
Yes,
this
sir.
kind of actually highly nonlinear issues we generally face with hyperelastic material.
Yes,
This
yes.
you
Like,
can try, sir.
yes, sir.
This
Yes, sir.
thing you can try nonlinear and mesh adaptivity.
Yes, 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 yes.
And there you can give the, if you are using tetrahedrons or any other, whatever the element, you can provide the value there,
Yes, yes, yes,
the
yes, yes.
criteria to avoid the distortion.
Yes, yes, yes. Okay, okay. Thanks. Thank you, sir. And one more issue is there. How we can directly connect if we are getting this kind of issues like that through mails on, or is there
Yes,
any
sir. Yeah.
platform where we can discuss directly?
Yes, sir. I will provide our company support mail ID, ansys.support@arkinfo.in. So if you have any queries or if you want any support, you can reach out to this mail ID. And also I'm providing my mail ID as well.
Yes, 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 sir.
Yes, sir. You can, in case if you need any support or help, you can reach out to this mail IDs. You
Sure,
can
sir.
write to ansys.support and you can keep me in CC for quicker response.
Yes, 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 sir. Thanks a lot, sir.
Thank you, sir. So if anyone else have any queries,
And sir, can you just provide these slides if possible for you? It's like something personal, but if it will be helpful for us if you will share your presentations with us.
sure, sir. Like I can't share all the slides; it is confidential. But you
Yes,
can
yes.
mail me like whatever the topics that you are like interested. I will share the related slides and information to you.
Okay, okay. Thanks a lot, sir.
So we provided the feedback form in the chat box. Uh, just, just so kindly fill the feedback. Your valuable feedback will help us to improve our webinars, and you can also mention like what you are interested in any particular topic. So in case while solving the problem, if you need any support, you can reach out to our mail IDs. And hope you no one has. We'll close the session. So thank you everyone for attending our session. So
And sir, when will be the next session related to these nonlinear Ansys problems and issues? It will be there
yes, sir,
on nearby.
nonlinear dynamic analysis we will plan maybe in next quarter of then look at.
Okay, okay,
So
okay, okay.
yeah. So nonlinear dynamics, both implicit and explicit. For implicit, we will take one webinar, and for explicit dynamics also we will plan for maybe in
Okay, okay,
next coming months.
okay, okay. Thanks a lot, sir.
Thank you, sir.